Hello, O Morgan Labs. Circular motion, tension on a string. So you have a problem like this. You have a mass spinning on a string. Omega is 4.2 radians per second. That's the angular velocity. You have a radius of 3.5 meters. Your mass is 0.65 kilograms. And you want to find the tension T in the string. Okay, step one. What are we trying to find? We're trying to find our tension T in the string. So that's going to be the first step. Everything's going to be revolving around finding tension. Step two, identify concepts, equations, and equations from your known and unknowns. This is where we think about, okay, I'm trying to find tension. What concepts, equations relate tension? What's my scenario? Okay, it's a spinning object spinning on a string. Okay, circular motion. What are my equations of circular motion? Okay, I forgot to mention, incidentally, we don't have any gravity. No gravity in this problem. That makes everything simple. This is the simplest problem you can have so you can understand the concepts involved with circular motion. Uniform circular motion. You're not accelerating. You're going around. It's like the earth spinning. It's just rotating. It's got a constant speed, right? Uniform circular motion. Zero gravity. Don't have that complication. So remember that. Okay, so we're going to use free body diagrams and equations of circular motion to find our tension. You just know this just from doing problems and practicing it. It'll come. You just have to work problems. For free body diagrams, the key is asking, what does the mass feel? You have to kind of put yourself in the object's place. If you were this object and you were spinning around, what would you feel? There would be no gravity, so you don't feel anything pulling you downward towards the ground. You just feel this string pulling you. Strings always pull. That's an important fact in trying to get the directions right. And there you go. There's our tension pointing to the right because strings always pull. They can't push. They always pull. The other part of our free body diagram, we have to think about the thing is spinning in uniform circular motion. Constant angular velocity. So there is a centripetal acceleration. I know you're probably thinking, if you've never done this before, centrifugal force. But when we're talking about this in physics classes and dynamics classes, they'll bring up centripetal acceleration because when things get more complicated, it's easier just to think about the motion in this thing called centripetal acceleration that accounts for the circular motion. So let's draw that vector. This is a vector diagram, by the way, just arrows with representing forces in motion. There we go. Our centripetal acceleration always goes towards the center. That represents our change in direction at constant angular velocity. Just to reiterate, our force of gravity is 0. So that makes things complicated. We don't have an arrow going down for gravity. Keeping it simple. Okay, important step. We use Newton's second law. It's just not F equals ma. It's a vector equation. So we sum the forces. They equal the mass times your acceleration. Force is a vector, acceleration is a vector. So you have to break everything down in terms of direction. This is like a 1D kind of problem. We don't have the force of gravity going down. There's no y vectors. It's all in the x. X going to the right is positive. That's important because you need to differentiate between positive and negative. You'll see why later on. Okay, now we use our diagram in Newton's second law to set up our equation. We can drop the vectors because it's just going in one direction. The forces are on the left. Sometimes we call those the kinetics, the forces that make the motion. The motion itself is the kinematics. Motion, kinematics is on the right-hand side. Both of these arrows are pointing towards the right, and we defined right-directed arrows as positive. So left-hand side plus t equals mass times centripetal acceleration, and that's plus. I didn't put the plus in front of the terms because it's just implied when you don't write it down, right? But it's important. There you go. So we're halfway there, right? We have the mass, but wait a minute. We don't have the centripetal acceleration. If we just had the centripetal acceleration, we could solve for the tension. This is why sometimes physics problems are hard. They're actually one question, but you have other questions kind of embedded that you don't really think about until you kind of get into it, that you have to use to solve the problem. Okay, so we have to define this centripetal acceleration. Let's do that, and then we'll pull everything together, solve for tension. All right, so here's our diagram as far as the centripetal acceleration goes. When an object is spinning around at constant angular velocity is not changing. You have something called the tangential velocity. That's those blue letters there. If you cut the string, it'll want to move off in a straight line at constant velocity, right? Just following Newton's first law. So we define the centripetal acceleration as this tangential velocity squared over r. And that's your centripetal acceleration. But wait a minute. We are given omega. We're not given this tangential velocity, the velocity of the motion if the string is cut. Or a slingshot. You think of Daniel and Goliath. Or David and Goliath, my bad. Anyway, we don't have omega. So we need another equation to kind of figure out and relate omega to your tangential velocity. I know this is a little roundabout way of doing it, but you have to know the tangential velocity piece once you get more complicated and things start accelerating. Bear with me. Okay, so here we are. Your tangential velocity equals your radius of your circle. This is a perfect circle now. It looks like an ellipse because I'm trying to draw it in 3D and in perspective, but it's a circle, perfect circle. So you get the radius of your perfect circle that you're rotating around, and you get omega. That's your tangential velocity. Plug everything in. It's like an algebra problem now. So r omega is squared divided by r. That'll give you your centripetal acceleration. You simplify everything and you get centripetal acceleration equals r omega squared. And that's what we're going to use to solve the problem. See how easy that was? So at this point, you have all the information, all the ingredients to solve for the tension in a string that's spinning a mass at constant angular velocity or in uniform circular motion. If you want to see more, I'm going to expound a little bit more on centrifugal force, how if you want to use it, you can, but you can't use centripetal acceleration at the same time. You have to go either or. And if you want to see how I plug in the numbers, it's really simple. You know the mass, you know the radius, you know omega. Just plug in everything and you get your answer. So go down, like and subscribe, download the video. Yeah, so hopefully this helped you, and I'll see you next time.